So how do we get the delta H? In order to get the delta H, remember we use the equation 3-1, 3-2 to calculate the delta H out of the heat of a combustion. So we must get the heat of a combustion to calculate the delta H, okay? Then how do we get the heat, the energy? We can see there is a temperature change. Then how do we get the energy? In our homework one that we did that exercise, then we can use the mass times the heat capacity times the temperature change, then we can get the heat of the combustion. And in this case, the challenge is we can probably measure the amount of water we put in there, and we can probably measure the amount of stainless steel that's in there. But how do we get the overall heat capacity? Because there will be a lot of stuff inside. There will be some air, there'll be some water, there'll be some stainless steel, there will be the fuse we use and the electrodes. So it's a complicated system. How can we get a single value? We can probably measure the mass of each of them, but how can we get a single value of a C here? So we use something we already know to calibrate the calorimeter so we can figure out the C. And actually figure out the C is relatively difficult because we have different materials inside. So we will combine M and the C. We'll call that W. That's combination of N and C. And we use something, it's easy to get and easy to measure with known heat of a combustion to calibrate our calorimeter. So we use benzoic acid to calibrate the calorimeter. We measure certain amount of benzoic acid. So that's 2 electrodes. So, and the white cotton fuse is attached to on the surface of benzoic acid. When we put that into the bomb, when there is electrical current that goes through here, the fuse will get burned and that will ignite the benzoic acid, okay? So in this case, we use that as our standard. We can make 3 trials of benzoic acid and calculate how much heat we get from the known value of combustion. In here, we still have this equation, Q equal to, so now we combine M and C as W, Q equal to W times delta T in this case. And this Q is the combustion from the benzoic acid. We can calculate based on the molar heat of combustion and the weight of a benzoic acid, right? And we can measure delta T. So right now we need to figure out the W value. The W will be equal to the heat of a combustion of benzoic acid. And there are some correction terms, okay? So E1 will be the correction for nitric acid formation. Before we put in excess amount of oxygen, there's already air inside. In air, there's 78% of nitrogen and 22% of oxygen, right? So in the elevated temperature, the nitrogen will react with oxygen and form nitrogen dioxide. And eventually, when there is water, the nitrogen dioxide will form nitric acid. So we need to make some correction because of that chemical reaction. I'll just provide this value so you can use 8.5 calorie to correct that reaction. And E2 is usually the correction for sulfur. And in our case, we didn't introduce any sulfur, so there's 0 for us in this case. And E3 is the correction for the fuse combustion. We use a cotton fuse here, and the combustion value is 50 calories. And in the handout, you'll see people use iron fuse. So the correction for iron fuse is different. We'll just use the 50 calories in our case. The calculation handout is on Canvas, and also the standardization files together with other combustion data is also on Canvas. So you'll be provided the mass of a benzoic acid, and you will need to look up the heat of a combustion of a benzoic acid in literature. So that's H. You need to figure out H in literature, and then you'll be given M as a measurement. And then now you have the value from E1, and E2 is 0, and then you have value for E3, and the T here will be your measurement, the temperature rise. So you can calculate the W, right? So when you calculate the W, you can continue your experiment to burn TTCC and cyclohexane as well. Okay, so in the experiment, you'll need to run 3 trials of a benzoic acid to calibrate the bomb. And then when you calculate the W values, you can run combustion trials for cyclohexane using the volatile liquid technique. So the cyclohexane is a liquid. The benzoic acid is solid. The solid is fairly easy. We just put the solid inside that cup and make sure the fuse is in contact with the solid, then you are down. However, if you have a cyclohexane, that's going to be a little complicated. We're going to put a tape on top of that cup, okay? And we will use a syringe to inject, so we poke a little hole onto that tape and inject the cyclohexane inside, and then we can measure the weight, and we will have the tape, the fuse in contact with the tape in that case. So the cyclohexane and the tape will get burned inside the bomb, okay? In this volatile technique, we introduced something new, right? We introduced the tape combustion inside. So we need to make a correction of the tapes. And it's difficult to calculate the heat of combustion of the tapes if we just use very little tape, right? So we will run another tape correction measurement. In this case, you can see we use a lot of tapes together. We measure the weight of the tape and have it run 3 times inside a bomb. And we can calculate how much heat is generated. Since we already know the weight of the tape, we can calculate how much heat is generated per gram, right? Once we have that value, we can use that heat per gram in the case of a cyclohexane to make the correction. So 3 trials of a calibration that calibrate the bond colorimeter and then runs combustion trials for cyclohexane and TTCC. TTCC is also a liquid. Because they are liquid, we introduce the tape, which is also combusted inside the bomb. So we need to make the correction of the tape. Then we run the combustion trials of a tape to calculate the correction. Questions? Does that make sense?